Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. Welcome to Electronics. I am Mender Rosmina Zwin Abdul Rahim. Let's have a look on this hadith. Sal ibn Sa'ad reported the Prophet ﷺ said, "By Allah, that Allah guides a man through you is better for you than a herd of expensive red camels." Source Sahih Al-Bukhari. Sometimes in our life, there are people who come to us to seek help, to ask our opinion, our advice, or even to ask them to help, to ask us to help them in their studies, in their financial, that kind of things. And these people can come from our friends, our families, or brothers and sisters. But we should know that it is actually Allah that has guided them to come to us. It's actually a blessing which we should really appreciate, because as Allah mentioned in this hadith, that opportunity actually is much more valuable than a herd of expensive red camels. Okay, so nothing can compare to that. We are still on chapter 4, bipolar junction transistor. This video is related to chapter 4C, which consists of two subtopics. The first one is BJT voltage transfer characteristics, and the second one is BJT biasing. Voltage transfer characteristics is actually a graph representation showing the relationship between output voltage versus the input voltage. And this characteristic can be used to visualize the BJT transistor circuit. Okay, then in general, the voltage transfer characteristic can be divided into three states, which are the cut-off, active, and saturation. Okay, cut-off, active, saturation, these are the three modes in BJT operation, remember? Okay, so in order for us to understand further about voltage transfer characteristic, let's have a look on this particular example, where in this BJT circuit, we have two resistors, RB and RC, and we have VI, which is connected to RB. VI is our input voltage at the x-axis, and we have DC voltage 5 volt connected to RC. And where is V0? V0 is actually the voltage at collector terminal. This is the output voltage that will be the y-axis of voltage transfer characteristics. For this particular example, VBE value is given 0.7, beta value given 120, VCE saturation value is given as 0.2 volt. Now in this case, we are supposed to develop the voltage transfer characteristic, the curve of it. For voltage transfer characteristics, as mentioned further, we have three modes, right? The first one is the cut-off, the second one is the active, and the third one is the saturation. Let's have a look on the cut-off mode first, where we are considering the portion when VI is very small. VI is very small, it is not enough to turn on the diodes, or meaning to say it's not enough to turn on this BJT. So at this time, the current is zero, no current at the input, okay, at the base. Then obviously IC also should be zero, because IC equals beta IB. Since beta is zero, since IB is zero, IC also will be zero. Because of that, there is no voltage drop across this RC, meaning to say under this cut-off mode, V0 would be equal to 5 volt, because there is no voltage drop across RC. So in this case, our voltage transfer curve can be represented by a horizontal line like this with a value of 5 volt. Okay, now let's have a look on the second mode, which is the active mode. Okay, in this active mode, actually we can consider the KVL equations related to BE loop, as well as KVL equation related to CE loop. So if we consider the BE loop, remember the KVL can be done here, okay, in the BE loop, where we have 100 IB plus VBE minus VI equals 0. Then if we rearrange, we can get IB value, which is given by VI minus 0.7 divided by 100. Okay, from that KVL equation. Then let's have a look on the CE loop. Okay, CE loop is here, right? Then we can say from this KVL equation, ICRC plus V0 minus 5 equals 0. Then remember, IC actually can be represented as beta IB, and later it can be rephrased or rewritten. We can rewrite the equation in terms of IB, which is given by 5 minus V naught divided by 480. Okay, so what can we do next? Both equations here from BE loop and as well as equation from CE loop, we equate them together. Now we are having equation which is relating this VI to V naught. Remember our voltage transfer characteristic, the curve is about V naught versus the VI, right? So we want to see the relationship between these two. So we rearrange, then we are making V naught as the Y axis, obviously VI as the X axis. Remember Y equals mx plus C. So this should be the M, the slope, and this should be the Y interception. Okay, now so since we already have the equation between V naught and VI, let's go further. We know that the active mode is having a negative slope like that. Then if we go even further, actually by increasing VI like this, we'll come to a point where now the diodes in our BJT will become both forward bias. Okay, so under this condition, the BJT transistor now is entering saturation mode. Then it is already given before this, when it is under saturation, the value of saturation is actually equals to 0.2 volt. This is the output voltage under saturation mode. But the problem is we don't know what is the starting point of this saturation mode. So obviously in this particular case, we need to identify this Mr. X. We know the Y value because it's entering the saturation mode. The V naught should be equal to 0.2. So we are supposed to find for Mr. X. So how to find for Mr. X? Remember we already have the equation relating V naught and VI. We can substitute 0.2 volt into that equation. Then we are supposed to get VI in this particular case equals to 1.7 volt. Okay, so this should be the coordinate for the starting point of the saturation mode. Then if we go further, we know that V naught somehow will stay constant, okay, until VI equals to 5 volt. It will stay constant. So we have our saturation region here. So we already discussed cutoff, we discussed active, and we discussed the saturation region, showing all these three regions in our voltage transfer characteristics, V naught versus VI. Here is a similar example to the one that we discussed just now related to voltage transfer characteristics. So please use this example coming from Final Exam Questions, Semester 2, 2017-2018. For you to do your own self-revision. In this case, VCE saturation is given as 0.25 volt. The answer is given here, but again, you can do this example for you to do your own self-revision, okay? Now we come to the second subtopic, which is on BJT biasing. BJT biasing. But first, what is biasing? Biasing actually refers to the DC voltage which is applied to turn on the transistor so that this transistor can be operating under forward active region so that it can amplify input AC signal. Okay, so there are 4 keywords here in biasing. We apply DC voltage. Why we apply DC voltage? We want to turn on our BJT transistor because BJT transistor is an active component, remember? Then in order for us to do a proper amplification, we need to make sure the BJT is operating under forward active region so that we can amplify the AC signal. We need to have a proper biasing because we want to make sure the AC signal can be amplified properly. So if you can see from this voltage transfer curve for this particular BJT circuit, this is the AC signal. Okay, so as you can see here, AC signal is actually, in this particular example, is biased to be in the active region mode. Remember the one with the slope here is the active region, right? So you can see here the signal is being amplified properly. We are getting a full amplification. In contrast, let's have a look if the signal is not biased properly. So for example here, this AC signal, it lies between active as well as the saturation region. It lies between active and saturation region. So when we amplify this particular signal, we are going to get some kind of a distorted amplified signal. Yes, it's amplified, but somehow we are not getting a full amplification. So this is the effect of improper biasing. Talking about biasing circuit, actually there are three types that we are going to cover in this course. Actually there are many more types, but we limit our discussion on these three types. The first one is called as fixed bias biasing circuit. This is the simplest biasing circuit that we are going to cover. Then the second one is the biasing using collector to base feedback resistor. So as you can see from the circuit here, we have additional resistor which is connected between the base and the collector. The circuit is more stable compared to the first one. And the third one is called as the voltage divider biasing circuit. And this is the most stable circuit where it has two resistors here, as you can see, R1 and R2. Okay, now let's come to the first type, which is the fixed bias biasing circuit. So as I mentioned just now, it's the simplest transistor circuit where it have two basic resistors, which are RB and RC. And it has a single DC power supply, in this case VCC. And in this particular example, BJT circuit, we have C1. If you can see here, it is C1, okay, and another C is actually C2 here. Is that there are the capacitors C1 and C2. But for the purpose of doing the DC biasing, okay, the DC analysis of the circuit, whatever capacitors connected to our BJT circuit, we can replace it with open circuit. Because now we are considering DC, we can replace the capacitor with open circuit. So imagine if you replace this C1 with open circuit, meaning we are disconnecting this AC input signal from our BJT circuit. And if C2 is replaced with open circuit, we are disconnecting AC output signal from our BJT loop here. Okay, so in DC, capacitors are replaced with open circuit. Now let's have a look on this one particular example related to fixed bias biasing circuit. In this example, we have to determine few things. The first one is on the IB and IC values, and the second one on VCE value. Okay, there are two ways actually we can do to solve this. The first one is we can use KVL equations at BE loop and CE loop, and the second one we can also use the branch current equation and node voltage. It depends, okay. But first thing first, remember the capacitor we have to replace with open circuit, meaning we are disconnecting all the AC input and outputs from our BJT circuit. Okay, let's have a look. For the first one, when we want to find for IB and IC, in this particular case, we take note that in this particular example, emitter is being grounded, meaning to say VE equals to 0 volt. And we know that VBE is actually VB minus VE. VBE is VB minus VE. So since in this case VE is 0, we can straight away say that VB is actually 0.7 volt. So if you are using the branch current equation, in order for us to find for IB, IB is given as voltage here minus voltage to another end of the resistor here, right? Okay, so meaning to say IB is actually VCC minus VB, because voltage here is the base voltage, which is VB, divided by RB. Okay, so this is the branch current equation. 12 minus 0.7 divided by 240k, we are getting IB, and obviously from there you can get the IC. Actually for this one, you can also do KVL equation where you solve for the BE loop, where we do the minus VCC plus IBRB plus VBE equals to 0. Also you can get the same IB value. Then coming to VCE is also about the same thing. If you are using the branch current equation, we can say that in order for us to find IC is actually the potential difference between 12 to VCE value. Okay. In this case, the same thing. Since VE is 0, VCE is actually equals to VC. VCE is actually equals to VC. So 12 minus VC, okay, divided by 2.2K, then we can get the VC value. Then as I mentioned just now, VCE actually equals to VCE. VCE equals to VC, so actually we are getting the same answer. For the same thing here, we can do also caveat allocation where we consider the CE loop. You are supposed to get minus 12 plus ICRC plus VCE equals 0. If you rearrange accordingly, you are supposed to get the same answer. Now we come to the second type of biasing circuit, which is called biasing using collector to base feedback resistor. So where is the feedback resistor? This is the one, which is RB. It is connected between the collector and the base. Okay, that's why it's called as feedback resistor. Then it is just a simple circuit. The tricky part for this particular circuit is just on the current arrangement, because as we know, if let's say we have current flowing through RC, this current will be splitted into two, into IB and as well IC. IB is the current flowing at the base, IC is the current flowing at the collector, right? So at the end, IB plus IC, it will give us the IE. And as I mentioned, the tricky part for this particular circuit is actually the current that flows through this RC should be represented by IE. Normally the current flows through RC is IC, right? But in this particular feedback resistor circuit, the current flowing through RC is represented by IE. Why? Because later this current will be divided into two, IC and IB. IC plus IB is actually the IE. You only need to take note on this important part. The rest will just be the same. So let's have a look on the example related to our feedback resistor circuit. In this particular example, we are supposed to find for the value of RB and RC. IE is given, VCE given, we have VCC 10 volt and beta is given as 100. So we are supposed to find these two resistors RB and RC. That's the thing. So as I mentioned just now, the tricky part is here where the current flowing through RC should be IE, not the typical RC. Not the typical IC, the current flowing should be IE. So what do we do next? Remember, emitter is grounded. Again, VBE is actually equals to VB. Then from here, you can, because IE is given, then beta value is given, we can actually find straight away the value of IB. Okay. Then from there, actually, you can also find the value of IC accordingly. But for this particular example, remember, we consider the branch current equation for IB value, where IB is actually equals to the potential difference, which is the VC minus VB divided by RB. So in this case, VC minus VB divided by RB actually IB. And in this case, VC is actually VCE because emitter is grounded, and VB is actually VBE, which is equivalent to 0.7. So from there, we can solve for this, substitute accordingly, then we can find the value of RB for this particular example. Then later for RC, you can get the branch current equation for IE, because IE is flowing through the RC, remember? So IE is given as VCC minus VC divided by RC equals IE. So from there, substitute accordingly, we are supposed to get RC equals 7.7 kilo ohm. Now we come to the last type of BJT biasing circuit, which is called as voltage divider biasing circuit. For this particular type, as you can see here, we have two resistors connected at the base, which are the R1 and R2. Okay, then this is a very stable circuit. What does it mean? It means that the current and voltages, the IB, IC, IE and VCE, are almost independent of the variation in beta, meaning sometimes beta value might be changing, might be varied a bit depending on the temperature and other parameters, but the currents and voltages will remain just the same. It will be constant and independent of variations in beta. For voltage divider biasing circuit, the tricky part for it is actually, in order for us to do the DC analysis, we have to convert the input side of voltage divider biasing circuit to Thevenin equivalent circuit. because remember we are having R1 and R2. R1 is between base and collector, base and VCC, and R2 is between base and the ground. Okay, so as you can see here, R1 is between base and VCC, R2 is between base and ground. Okay, so from here we can simplify this particular network into Thevenin equivalent circuit, where R1 and R2 can be represented by Thevenin resistance, where it is equals to R1 in parallel to R2. Remember, in order for us to find for the Thevenin resistance, the VCC, we short circuit, remember, turn it off. So, meaning to say our RTH is R1 in parallel to R2. Still on Thevenin equivalent circuit, now we have to determine the value of VTH, Thevenin voltage. So in this particular case, VTH is actually the voltage across R2, and we can use actually voltage divider here. VTH equals to R2 over R1 plus R2 times VCC. Okay, so once we have RTH and then we have VTH, we can substitute accordingly the input side of voltage divider balancing circuit just now with the value of VTH and RTH here, and the rest of the components will just remain the same. So the same thing that I mentioned just now, instead of having R1 and R2 like this, we simplify it to Thevenin equivalent circuits. Now we have RTH and VTH. So we can include this RTH, VTH in the circuit as the representation of the input side. But then the rest of the components remain the same, where we still have the RC, we still have the RE, and VCC connected to the circuit. Let's have a look on one particular example related to voltage divider balancing circuit. In this case, we are supposed to find all the currents and the VCE value. All the circuit parameters are given. All the resistors R1, R2, RC, and RE. VCC 10 volt, beta is 100. So you know how to identify voltage divider balancing circuit by looking at the number of resistors. Since we are having R1 and R2 like this, so we know it's voltage divider balancing. So no choice, we have to do the Thevenin equivalent circuit. Okay, so we have to find for RTH and then we have to find for VTH. Then from there we can do the KVL equation circuit. Okay, because it's already replaced in the input side. KVL equation, we are supposed to get this KVL equation, VTH equal to RTH times IB plus VBE plus IERE. Substitute accordingly. Then remember, here we have two unknowns, IE and IB. So in this case, IB can actually represented by this beta plus 1 IB. Then leaving the only unknown here in this particular equation is IB. Rearrange accordingly, we are supposed to get IB value 21.62 micron. And obviously from there we can get the IC value. Then later we can get the IE. Then for the case of VCE, because we are supposed to find for the VCE as well, right? We just do the same similar like to the previous circuits where we do KVL at the CE loop. Okay, then we are supposed to get minus VCC plus ICRC plus VCE plus IERE. Then rearrange accordingly, you are supposed to get VCE equals to 4.8 volt. Okay, you can try to do this particular example later using the voltage divider balancing circuit, finding for the same thing, the currents and the voltage. The values, the answers are given here in the table. You can try to do your own analysis to find the same things. Here is another example related to voltage divider balancing circuit, where it's kind of design question where you have to determine the values of R1 and R2, where VCC given, IE is given, beta value is given, RE is given, and now RTH is given. Okay, so you should understand the concept of Thevenin equivalent circuit in order for you to solve for this example. So since we talk about the voltage divider balancing circuit where we have to convert the input side to Thevenin equivalent circuit, right? So the input side will be something like this, where we have VTH and RTH and the rest of the components just remain the same. Then remember, we can get the KVL equation from the BE loop there, okay, consisting of VTH and RTH. Then substitute accordingly, we are supposed to get VTH equals to 1.5 volt. Okay, then in this particular example we know that VTH is given by the voltage divider, remember, where we can calculate for VTH. So you substitute accordingly, but in this case we don't know the value of R1 and R2, okay, then times the VCC, which is 10, so we know that VTH is given by 1.5 volt in this particular case, right, 1.5 volt. Then later it's given that RTH is 33 kilo ohm, okay, then actually from there R2 over R1 plus R2, actually we can get from this portion, okay, which is equals to 1.5 divided by 10, isn't it? Okay, so that's why from here we can replace accordingly, substitute accordingly, 1.5 divided by 10 times R1, which is equal to 33 kilo ohm. So if you substitute, we're supposed to get R1 equals to 220 kilo ohm. Then obviously from there you can simply substitute into any of the equations to find for R2, which is given by 38.8. This is a design question where you have to find for the circuit parameters. In this case, we have to find for the values of R1 and R2. So that's all related to this video, chapter 4C, where we have two subtopics. The first one is on the voltage transfer characteristics, and the second one is on the three BJT biasing circuits, which are the fixed bias, the one with the feedback resistor, and the one with the voltage divider biasing. Okay, that's all for today. Thank you for now. Assalamualaikum.